this PCB from glcpcb.com.
GLC PCB is worldwide known for their quality and fast PCB production.
They are offering high quality PCB in very affordable rates. This makes GLC PCB is my favorite place to order PCB.
GLC PCB now started the SMT service for their customers. It means you can get your PCB assembled directly from GLC PCB. No need to worry about purchasing components and soldering them on PCB. GLC PCB SMT service will do it for you. GLC PCB also started 3D printing service. If you don't have 3D printer at your home or you need high quality 3D printing, so you can check out their 3D printing service in very affordable rates.
Welcome back to Aurora Tech Channel. Today, I will be reviewing the Sunlu T3, a budget 3D printer that claims to print at the speed of 250 millimeters per second. This is quite a bold claim for a printer in this price, a box frame. Additionally, the input shaping feature from Clipper firmware is necessary too. I am curious to see how the printer will perform at the advertised speed with this basic hardware and Marlin firmware. I would like to thank Sunlu for sending me this machine to review, and with that, the cube looks good with only some minor cooling issues, which is normal since the printer only has a 4010 cooling fan like an Ender 3. The X and Y surfaces are similar with minor cooling issues. The Z surface is a bit rough, but the overall dimensions are accurate. Next, we'll slice a 3D Benchy using normal speed as a baseline to determine the printer's best print quality. The Benchy took 1 hour and 47 minutes, which is similar to the Ender 3's 1 hour and 50 minutes print time. The quality is good, with no straining and decent cooling. There is no ringing when printing at a normal speed of 50 millimeters per second. Since the printer has a fast print mode, I will use the LCD screen to turn on this mode to print the same G-code file and see what happens. However, you can see cooling issues in many areas, the surface is not clean, and the ringing is bad. It seems this fast print mode just increases the print speed without making any other adjustments, which is not ideal, since everything can't be printed at such high speeds. The print is fast, taking only 39 minutes, but the overall quality is very poor, especially the horrible chimney of the Benchy. To see if we can achieve a better quality while printing quickly, I will create a new print profile in Cura to print at 250 millimeters per second. I will set the travel and infill to 250, the walk to 125, and the first layer to 40. The acceleration will be set to 1,500 millimeters per second squared to match the firmware settings. For small features, I'll slow it down to 25%, which will print at around 60 millimeters per second. As the fast print mode didn't give us our desired results, I will turn it off and just use the slicer to control the print speed. The Benchy takes 1 hour and 11 minutes. The quality is not perfect, but it is more presentable than the one printed with their fast print mode. The surface is not very clean, and there is some ringing, but it's not too bad and is acceptable for a fast prototype. Then, I will try printing a functional part with simple geometry, like a cable pass-through for the Ender 5 or Soval SV05, using my 250 millimeters per second profile to print a fast one first. This took 5 hours and 34 minutes, and the result is decent, so the part is still usable. I will then slice it again, using 50 millimeters per second in speed. Which took 11 hours and 31 minutes. which is 6 hours longer than the fast one, but the quality is better. However, for a functional part like this, saving 6 hours by printing the fast version is preferable. After that, I will attempt to print with ABS, which is faster than PLA since it doesn't require cooling.
This is a project I'm calling AutoScribe. This video is an overview of the project, the process I went through building and programming the machine, and some of the choices I made along the way. AutoScribe is a drawing machine which is able to draw pretty much anything. It was slow. And there were some retail versions, but I figured, how difficult could it actually be to build one of these myself? And the answer I found after actually doing it was, it's pretty difficult, but I think that's why it's worth talking about. As an overview, before I get into the details, the way it works is I start with a special type of image file called an SVG, then I convert the image file into a set of instructions for the drawing machine, and then send those instructions from my computer to the Arduino. Then the drawing machine will move its 3 motors to draw the image. The first step was buying all of the parts and creating the hardware. I found a couple of really helpful websites, especially one Instructables page, which was my main source of inspiration for the physical design of the machine, and I'll include a link to this. The base is made up of 2 stepper motors, the exact same things you might see on a 3D printer, connected with a pair of metal rods. The arm is made up of 2 more metal rods, a servo motor to raise and lower the pen, and a hub to connect the arm to the base. A timing belt is fixed at the side opposite the pen, looped around the first motor, free to move around the end holding the pen, looped around the second motor, then fixed back at the end opposite the pen. This style of using a single continuous belt to control both axes is called Core XY, and this specific design can be called a T-bot. To move up, both the stepper motors have to spin clockwise. To move down, both have to spin counterclockwise. To move right, the top must spin clockwise while the bottom spins counterclockwise, and to move left, the top has to spin counterclockwise while the bottom spins clockwise. If only one of the motors spins, then it moves diagonally. I think this layout for the motors is pretty cool because it's not immediately intuitive how it would work, but it's great because it keeps the heavy stepper motors at either end of the base and they can both remain stationary. I relied on other websites when coming up with the physical design and mostly made small improvements like making the hub where the axes connect a bit more streamlined and remodeling the ends with a wider base and adding rubber furniture feet to increase grip and reduce vibration. Most of the websites I referenced all used the same software, GRBL, an open source project for CNC motion control. The main difference with my project is that I designed all the software for both the Arduino and my PC from scratch. When designing the code for the drawing machine, I decided to make the problem a bit simpler and focus on making a machine that can draw straight lines. Easy, just figure out the endpoints of the lines and then the machine can go to each of them in order. But how does this happen exactly? Since the stepper motors do just that and step a certain distance, if you zoom into the tip of the pen real close, there's really only a couple of choices to make for the movement. It can move up, down, left, right, or diagonally one step. That means we just have to figure out what combination of these movements will get the pen from the starting point to the ending point. This seems like a pretty easy problem if you're going straight up or right or exactly diagonally, but what if you're going to a coordinate point somewhere like 8, 5? That has a strange slope where you'd have to do a weird combination of movements to get from the start to the end. How can we easily figure out that sequence of step-by-step movements but for any possible point? Since each step of the motor is really just a movement on this grid, then stepping from point A to point B is more or less the same as trying to draw a line with pixels, which is a problem someone already solved 60 years ago. Bressenham's line algorithm was designed in 1962 to draw lines with pixels on a computer monitor by just keeping track of a couple of numbers and using only basic math. I implemented a variation of the algorithm that I optimized for. This is a project I'm calling AutoScribe, counterclockwise while the bottom. The code for the drawing machine, so there's really only a couple of choices to make for the movement. It can move up, down, left, right, or diagonally one step. That means we just have to figure out what combination of these movements will get the pen from. That has a strange slope where you'd have to do a weird combination of movements to get from the start to the end. How can we easily figure out that sequence of step-by-step movements but for any possible point? Since each step of the motor is really just a movement on this grid, then stepping from point A to point B is more or less the same as trying to draw a line with pixels, which is a problem someone already solved 60 years ago. Bresenham's line algorithm was designed in 1962 to draw lines with pixels on a computer monitor by just keeping track of a couple of numbers and using only basic math. I implemented a variation of the algorithm that I optimized to run on the Arduino so that the pen can move quickly and smoothly across the page. Now, how do we figure out what lines to draw? There's a type of image file that can help called an SVG image, or scalable vector graphic. Unlike JPEGs or PNG files, which are called raster images and store individual pixels, PNG images basically store a series of lines or curves. Generally, SVGs are used because you can easily resize images much larger or smaller without losing any quality. For the purposes of this project, SVGs are nice because they already have the list of lines that make up an image. But a drawing machine that can only draw straight lines is pretty boring. SVGs also store equations for more complex shapes made up of things called Bezier curves. If we can break up a curve into a bunch of tiny line segments, then we just need to send the drawing machine each of those straight lines, and it can effectively draw twists and turns. At first there's the concern that it would take a ton of line segments to represent a curve without the image appearing too choppy, but there's a limit to how precise the stepper motors are. So I took advantage of this and divided the Bezier curves into as few line segments as possible, while still maximizing the resolution of the motors. Now, we have a way to get a list of coordinates to draw an image and make a machine that can draw straight lines. The computer has the SVG image and all of the info, but the Arduino is what controls the drawing machine. The last step is to combine those two things together. As the computer starts sending drawing info over their USB serial connection, the first thing it does is send a command signal. This tells the Arduino that it's about to start drawing an image, so it knows that the next pieces of info it gets are coordinate points for an image, rather than instructions for one of its other features. I also included features for the drawing machine, like fine-tuning the height of the pen in case the drawing surface changes, or manually controlling the pen like an Etch-a-Sketch with the arrow keys and the space bar. When the Arduino gets the drawing command, it starts listening for coordinates from the computer and keeps a list of them as it's drawing. I really enjoyed working on this project because of a combination of software, hardware, 3D modeling, and just intuition that had to go into creating the drawing machine. The best part was the moment when the final design started working. The first real complex image I had the machine draw was a little picture of a dog, and as I kept testing it with more and more images, it was so satisfying knowing that it could draw just about anything. In the description, I'll also link to the GitHub page for this project, where I've included all the code for the computer software, the Arduino program, a complete list of the hardware, and all of the SolidWorks 3D models I created. Thanks for watching.
Hey, what's up guys? It's Dr. D Flo and welcome to part 4 of the large format 3D printer build. We're going to do a lot of printing in this video, but first I need to tie up some loose ends and then install the pellet conveyance unit because this machine needs a constant flow of plastic. And with that, let's get started.
Dr. D Flo.
Could not wait to fire up the printer. Play the software side of this build, but one feature of the Duet 3D firmware that I want to draw your attention to is its ability to run custom background processes when it's idle or even printing. In this case, I'm having the Duet check the temperature of the bed and the extruder every 10 seconds. Of how the air flows through the line back. These constrictions form high-velocity air jets, which, as we know, form a vacuum according to the Venturi effect. Besides the solenoid, which starts and stops the vacuum, the unit will only be on every now and then, and I'm hoping to get away with my current setup. Let's take a look at what I have in my garage. Go. FM, I'm gonna have to clean that up now. I have attached the hose, which will carry the pellets to the extruder to this 3D conveyance unit. So, the best solution I could come. It is incredibly sturdy. I weigh 170 pounds, and I didn't feel the chair flex when I sat down. If a nice office chair 10 on the comfort scale, then I would probably give this one a 7. Similar comfort level to patio furniture. But before we talk more about the design, let's discuss the printing parameters and operating costs. This was a true base mode print. One perimeter extrusion line was laid down as it spiraled up in the Z direction. The height of the extrusion was 3 millimeters, and even though I used a 5 millimeter nozzle, through cranking up the extrusion multiplier, I was able to achieve an extrusion width of about 10 millimeters. During some preliminary testing, I determined that this large of an extrusion width was necessary for the chair to be strong enough. Here is a partial print where I used a 5 millimeter extrusion width. It's obvious that this would not make a very good chair. My print speed was 20 millimeters per second, which may sound slow, but the volumetric output was about 1.1 kilograms per hour, or about 2.5 pounds per hour, which is 25% higher than the suggested max output of the extruder listed on Massive Dimensions website. The total print time was 18 hours. The flow rate in print time suggests that the chair weighs quite a bit. I can use this scale to determine its weight. At about 17.85 kilograms, or 40 pounds, you don't have to worry about this chair blowing away. Every 1 kilogram of pellets with the 1% colorant costs about 8.
红墨家的垃圾规则，谁最后一个装满，谁就要去倒垃圾。为了逃避劳动，他们疯狂试探垃圾桶的极限，只要还没溢出来，就不算装满。垃圾逐渐堆成了行为艺术，连一根香蕉皮都挂不上。巴特微微一笑，竟然用订书机作弊。第二天，红墨发现连一张纸都会让垃圾崩盘，他把包装纸回收利用，当便利贴。这是比拼耐心与智慧的时刻，千万不能认输啊！红墨咒骂时运不济，但规则就是规则，他要把垃圾倒了。门外的垃圾车刚好路过，他们每周来一次，门口有啥就收啥，错过就要再等1个礼拜。红墨疯狂的喊叫，他们不停车，喊叫逐渐升级为破口大骂。他们听到后立刻回来，小次郎，你刚才骂什么来着？垃圾工跟红墨干了一架，并且再也不收他们家的垃圾。丽莎说：“赶紧道个歉吧。”但红墨在这种事情上经常有骨气，就算家里成了垃圾填埋点，我也不会道歉的。从今天开始，我和巴特负责处理垃圾。就这么过了一阵子，垃圾围住了房子。孩子们出门上学前，马吉要先用诱饵把老鼠支开，否则谁也别想安全地跨过这片垃圾海。生活如此艰难，但也无法击垮红墨。他可能没什么上进心，但在赌气方面却有着超乎常人的毅力。在某个清晨，起床后的红墨发现门口的垃圾不见了。他在早餐时间
Almost a year ago, I released a very popular video on threaded inserts for 3D prints, on which I got a ton of suggestions and comments. One of them was that I used for my tests a type of threaded inserts that I found on my local eBay, which looks quite a bit different than the typical ones that you find on AliExpress or also on Amazon. Despite the different look, do they really perform differently, and how easy are they to use? This is something I tried out for this video. Did you also try out inserts? Then let us know your experience down in the comments. For the last test, I also used M5 threaded inserts, whereas it seems that most of you rather put M3 inserts in your 3D prints. So I purchased similar M3 threaded inserts as last time from the same eBay shop. I also purchased a set of these press inserts on Amazon that probably are rather used in injection molding. I also was bombarded with ads for these Rutex threaded inserts on Instagram lately that claim that they are especially designed for 3D printing, so I also bought a bag of those on Amazon. Not a sponsor, by the way. They do look kind of nice, though I think that rather than being specifically designed for 3D printing, those are just proper heat seat inserts, but we'll find out